Hey y'all, so today we're going to jump straight into an example and a practice problem, kind of building off of what we did yesterday. So let's go ahead and get started, and then you will do a practice after I do this example. All right, so remember, you're going to need to know what we did yesterday. So if you haven't already watched that video, make sure you watch that, and then you'll be ready for today. All right, so let's get started. Let's read this question. Example 1. Find all values of p so that x of p is a solution. So we're trying to find y equals x of p to be a solution to the differential equation, this differential equation that's given, 3x dy dx equals y. All right, and if you recall what we did yesterday, we started by finding things. We need to find things that we can plug in to plug in the differential equation, plug into the diff EQ. Okay, so we need to find things that we can plug into this thing. So do we have anything given to us about x? We know y is x of p. It's going to be hard to deal with isolating x there, so let's not stress about that. But we do have a y given to us, so y is x of p. We can very easily replace that y with x of p. And then we also know that we need the first derivative of y right here in this diff EQ. So let's go ahead and write these things down. We know y equals x, no, I keep saying x of p, x to the p. Y equals x to the p, sorry about that. And then dy dx, the derivative of y with respect to x equals, and we're going to use the power rule here. So we have x to some constant, some number, p. So the power rule for the derivative, we have p x to the p minus 1. That's our derivative. All right, and now let's go ahead and plug those in and see what we've got. So we're going to plug those into our differential equation. We have 3x, and then instead of dy dx, I'm going to put p x to the p minus 1. And then we have equals, and instead of y, I'm going to put x to the p. Okay, cool. Before we simplify any further, we need to know what is this exponent on this x, and that exponent is 1. So let's go ahead and rewrite that. We have 3x to the 1, and you'll see why I'm writing it like this. Actually, let's write 3x. Okay, let's just go with this. 3x to the 1 times p times x to the p minus 1 equals x to the p. Okay, so I rewrote it this way because we have the same base, x, here. Those are multiplying. So if you recall, if we're multiplying the same base, we add the exponents. So here this would turn into 3p x to the 1, add your exponents, plus p minus 1 equals x to the p. All right, 1 plus p minus 1, well, the 1's cancel out, 1 minus 1. So all we're left with is 3p x to the p equals x to the p. I'm trying to isolate p, by the way. If we look at like what we're asked to find, we're trying to find all values of p. So we want to like get p alone. Find p so that this thing is a solution. Okay, so now to isolate p further, I'm going to divide both sides by x to the p. So we have 3p equals x to the p divided by, these cancel, x to the p divided by x to the p is 1. And then last thing we got to do is divide by 3. So p equals 1/3. This is the value of p that will make y equals x to the p a solution to this differential equation. All right, so now that I've done an example, I want you to try on your own. Let me scoop this up. All right, so you're going to try this one on your own, and then I will walk through it so that you can know if you did it right. All right, go. Cool. So now let's go over your practice problem. So we are trying to find all values of b so that y equals bx, square root of bx plus 3 is a solution to this differential equation dy dx equals 5 over y. Okay, we're going to do the same thing as last time. We want to find things to plug in. So we were given y again. We can plug in y equals square root of bx plus 3. And we also know that we can find dy dx. Sorry, we're going to plug in the y right here. We also can plug in something for dy dx. Let's go ahead and find the derivative of y with respect to x. And before we do that, I'm going to rewrite this. So this is for the derivative. The same, actually, let's do this in blue because we are not taking a derivative yet. We're just like saying what this is equal to. This equals bx plus 3 to the 1/2, right? Okay, so now we need to take a derivative. This is a chain rule derivative. So we're going to say u equals my inside, I'll do it over here. U equals my inside, bx plus 3. And v equals u to the 1/2. Take the derivative of both pieces. B is just a constant. So this derivative is that constant b. And then derivative of u to the 1/2 is 1/2 u to the negative 1/2. And then we need to plug back in for u. So u was bx plus 3. This turns into 1 over 2 square root of bx plus 3. And you can see I moved this u to the negative 1/2 down here because it's negative, and then turned it into a root because 1/2 is my exponent. Okay, cool. Don't forget to multiply these. So the derivative is this times this. So dy dx equals, the b is going to go on top, right? Big constant times fraction goes on top. So we have b over, and then 2 square root of bx plus 3. Cool. So now that we have two things that we can plug into our diffie-q, we can plug in y and we can plug in dy dx. Let's go ahead and do that. So this differential equation turns into dy dx is b over 2 square root of bx plus 3. And then we have equals 5 over, and instead of y, I'm going to put square root of bx plus 3. Okay, cool. All right, and we are trying to find b again, so let's isolate b. The first thing that I would do is I would multiply the bx plus 3. You can multiply either one of them. I'm just going to multiply this one to this side. So times square root of bx plus 3 times square root of bx plus 3. And they will cancel on both sides. So you get b over 2 equals 5. And then multiply 2 on both sides, times 2 times 2, b equals 10. And that's it. We found the b that makes y equals the square root of bx plus 3 a solution to this differential equation. All right, cool. Let's move on. So now today's notes are going to be, I think, a decent amount shorter than yesterday's, so yay. The next thing we're going to do is we're just going to do 2 diffie-q examples, FRQ style ones, and then we're done. And you'll do your mastery check. Okay, so now we need to see like what kind of equations are we going to be looking at on the AP exam for differential equations type problems. So, or what kind of FRQs, sorry. So here's old FRQ, 2014, AP Calc AB. This is just one part, it's part C, and before we start, I can tell you this part was worth 6 points. Yeah, this was worth 6 points, just this one part. So let's go ahead and work through this part and see how many points out of 6 can we get. Actually, yeah, I want you to practice first. So go ahead and take a shot at doing this, and then I will show you exactly how I would do the problem, and then you'll be able to see how many out of 6 points were you able to get on your own. So if you're struggling, go back to yesterday's notes. let's just work through the very first part before you start. Consider the differential equation. So we have a differential equation, dy dx equals 3 minus y cosine x. Let y equals f of x be the particular solution. So we're trying to find what does y equal, that's our particular solution, to the differential equation with initial condition f of 0 equals 1. The function f is defined for all real numbers. Alright, so then find y equals f of x, the particular solution to the differential equation with this initial condition. We're trying to find the particular solution. So remember that we wrote down a bunch of steps. I would go work through all of those steps, go back to your notes, see how many points you can get, and then we'll go over it. Okay, let's go over this diff-EQ. So yesterday I used different colors to kind of like show the first step, which was separation. So I'm going to do that again today. So we have dy over, and y'all be patient with me, over dx. Thanks for being patient with me. Dy over dx equals, hold on one second. There we go. Okay, dy over dx equals, and then the y piece that we have is 3 minus y, and the x piece, oops, y'all, I meant to make this dx in orange. Let's make x in orange. So dy over dx equals 3 minus y cosine x. Okay, we need to get all the x's on one side, all the oranges on one side, all of the blues on one side, all the y's on one side. So the first thing you should always do, multiply dx on both sides. Always. They'll cancel out on this side, and you have dy equals, and then 3 minus y cosine x dx. Cool. So then the next thing we want to do is get this blue piece, this y piece, onto this side, and you can see that these operations right here are multiplication, multiplication, so we're just going to divide 3 minus y on both sides, and remember I told you to write it like this, 1 over 3 minus y dy, because we know we're going to integrate eventually, equals cosine x dx. Cool. Okay, so now that we have separated, we can go on to the next step, which is integrate both sides. So I'm going to do that in green. Integrate. This is a U sub problem. Yesterday I kind of like said it was U sub and then didn't show the work when it was. So I'm going to actually show y'all. U equals 3 minus y, and then du dx equals the derivative of this, which is negative 1. And that means that du dy, right? Because we have y as a variable. Dy is going to equal 1 over negative 1, 1 over negative 1 du, which is equal, that's just equal to negative 1 du. So now we can like plug that in to this integral. I'm going to do that over here. So let me show you what I'm doing over here. We have, this turns into the integral of 1 over u, because 3 minus y is u, times dy is now negative 1 du. So that is the same as the integral negative 1 over u du. Okay, the integral of 1 over u is natural log absolute value of u, but don't forget this negative, and then plus c, but again, we don't put plus c on the y side for diff EQs. So now we just need to plug back in for u equals negative natural log absolute value. If we go back to what u was, that was 3 minus y. Sweet. So anytime you have like 1 over a single, like, I guess, piece of a function, u sub is probably your best option, and you'll get a natural log. So we have this integral is negative natural log absolute value 3 minus y, and then equals, now let's actually do this piece, the integral of cosine is sine x plus c. Alright, cool. Now that we have got gotten that, we need to isolate y. But before we isolate y, let's like go ahead. Actually, we can start. Actually, no. Let's isolate, or before we isolate y, let's talk about this absolute value thing really quick. So if you look at this problem, we're trying to find the particular solution with the initial condition 0, 1. If we were to plug in 0 for x, sign would turn into 0, right? And then you'd have some constant over here. And if we were to plug in 1 for y, this inside would already be positive. Like imagine plugging in 1 for y, you get 3 minus 1, that's 2. It's positive already. So do we need to make it positive? We do not need to make it positive. The absolute value bars are saying, hey, you're going to have to make this positive sometimes, but in this case, we don't. So we actually can take the absolute value bars away. So let's go ahead and do that. And that's true for pretty much every diff-EQ problem that involves a natural log out of the integral. Okay, now let's work on isolating y. So we need to use, first let's get this negative off. So we divide both sides by negative. Divide by negative 1. And we have natural log of 3 minus y equals negative sine x. And then positive c divided by negative 1, we don't really know what c is, so we're not going to let signs affect c, like sign changes. So we're still just going to write plus c. Okay. Now we need to convert to get y out of the log. We need to convert this to exponential. So the base is e, and then we do like the chubby hand, e to the other side, e to the negative sine x plus c equals, and whatever's inside of the log, 3 minus y. Cool. I'm going to add y, and then actually let's simplify this. Sorry, y'all. So let's simplify this side first. Remember, we can split this into two e's. Because of the addition, this is the same as multiplication, e to the negative sine x times e to the c equals 3 minus y. E to the c is just one big constant. We talked about that yesterday. So that's just a constant. So we're going to say this is the same as c e to the negative sine x equals 3 minus y. All right, so now I'm going to add y over, and at the same time, I'm going to subtract this over to here. So we have y equals 3 minus c e to the negative sine x. Cool. We have isolated y. Okay, and I want to tell y'all about a trick really quick. So sometimes, so the next step is to here, let's talk about the next step first. The next step is to plug in our initial condition. That's normally like the order we go in. We do all of this. We get, what's it called? Separate. We separate here. We integrate. We isolate y. We plug in our initial condition. Okay, so here's the thing. You can switch. I'm going to put a little note, and I want y'all to put like the same note. You can switch the steps, and I'm going to like name the steps. You can switch the steps isolate y and the step plug in. I'm going to say call it IC for initial condition to find C. Those were two of our steps from yesterday. You can switch those steps if you want. And then do a little dot dot dot. Sometimes it makes the problem easier. And we'll actually see that in a second. Sometimes it makes the problem easier. So we'll see that on our next example. For this one, we didn't need to switch them to make it easier. So let's keep going. I just wanted y'all to be aware of that and put that into your notes. So let's keep going. We have the initial condition, IC is what I called that down here. F of 0 equals 1. That is the same as the point 0, comma 1, right? Okay, so I'm gonna bring it over here, and we're gonna plug in the point. I'm gonna put a note, we're plugging in this point, 0, 1. Okay, so we have y is 1, So we'll get 1 equals 3 minus c e to the negative sign, and then instead of x, we're plugging in 0. Okay, let's continue to solve. So we have, or simplify, 1 equals 3 minus c. Sign of 0 is 0, so we have e to the 0. Cool. So 1 equals 3 minus e to the 0 is 1, so we just have c here. And then I'm going to add c over here and subtract 1 over here at the same time. So we have c equals 3 minus 1, which is 2. Awesome. And we are so close to being done. Now we need to write our particular solution, which always starts with y equals. And then we copy this. We combine these two things. We combine our isolated y and our c. So we have 3 minus c is 2, e to the negative sine x. That is the particular solution to this differential equation. Okay, really quickly, let's go through how the points were distributed, and you can see how many points you got on this diffie Q. Okay, so let me get these side by side. The first step was to separate. If you correctly did separation of variables, you get a point. So let me show you where that point is. Separation of variables, that's getting to here. I guess it's kind of hard because I always integrate in the same step, but that's getting to here, but without the integral signs. 1 point. Okay, cool. If you correctly take each antiderivative or integral, you get a point. So the first point will be from this antiderivative. Make sure that you had that negative sign, because that's often missed, and you will not get the point for the integral if you did not have the negative sign. And then the second point is for this integral, sine x. They're being very generous on this specific FRQ, but they're not always this generous. They give you a point for the constant of integration. That's giving you a point just for having plus c here. So right now we're at 1, 2, 3, 4 points so far on this diffie Q. Your next point is using the initial condition. I wanted to remind you, we can use it now. We're allowed to use it right now if we want. We could just like plug in the initial condition right now. I always like to try to isolate y first and then plug it in. So we plugged in our initial condition over here. You get a point for correctly, or for just using that initial condition, plugging it into whatever you had. Even if what you had over here was wrong, like whatever you got right here, if you plugged in your initial condition, you get a point. Okay, so we're up to 5 points. And the final point was for solving for y. So correctly isolating y, and you actually do need to have the initial condition. This has to be like exactly correct to get that final point. It has to look just like this with the c equals 2. All right, so try to add up really quick, add up your points, see how many you got the first time you tried it. And tell me how many you got. Also, just as a reminder, since these questions are often worth, usually they're 4 to 6 points. Like, they won't always be 6. Sometimes they won't be so generous with the antiderivatives or giving you the constant, but these will be 4 to 6 points usually. So this process, solving a differential equation or solving the particular solution, is very important to be able to do. Okay, let's move on. We have one last thing to do, which is this very last diffie Q example. I'm not going to make you practice this on your own because it's kind of a different style of diffie Q FRQ. It's not what we've seen or we've been seeing in the notes. Okay, so let's talk about this. I still think a lot of y'all could probably still crush this. This is the entire differential, or the entire free response question, so it's parts A through C, and it's out of 9 points. We will break down the points after we complete the FRQ. Okay, so let's get started. We have solutions to the differential equation. So, we have this differential equation, dy dx equals xy cubed, also satisfy this differential equation. This is the second derivative, so let's take some notes. This is the second derivative. This is the first derivative. A lot of students can look at these and get a little stressed out, but don't be. It's just the first derivative, second derivative. It's like saying y prime and y double prime. They're just writing it in this form. Okay, so solutions satisfy these two equations. Let y equals f of x be a particular solution, which is what we've been finding, particular solutions, to the differential equation, this one, dy dx equals xy cubed. So y equals f of x is that particular solution. And then you have that point given to you. They did not say with the initial condition, but this is your initial condition. And it's a point, 1, 2. Okay, cool. Let's look at what they're asking for the first part now. Write an equation for the line tangent to the graph of y equals f of x at x equals 1. Okay, so we should pick out some keywords here right off the bat. It says the line tangent to. So when you're writing an equation for a tangent line, let's take a note. Hold on, y'all. Sorry, I'm trying to find my, there we go. Okay, so when you're writing an equation to a tangent line, part A, tangent line, you need two things. You need a point and you need a slope. So I always look for the point first. Were we given a point? Write an equation for the line tangent to the graph at x equals 1. Did they tell us a point on f at 1? Yes, they did. The point is 1, 2. Cool. So they did give us a point. And then the slope is going to be dy dx. That's the derivative of y with respect to x. So did they give us a derivative? Yes, they did. dy dx. dy dx, except this, we need the slope at this point. So we're going to write, we need the slope at 1, 2. Sorry if you can't see that 1. At 1, 2. Now let's actually plug in 1 and 2 into our slope equation. So dy dx here, I'm going to write dy dx equals xy cubed, right? That's our slope, but we need it at this point. So let's go ahead and plug in this x, this y into here. So we have 1 times 2 cubed, which equals 8. Okay, now we're ready to write our equation of our tangent line. We do the equation of a line, y minus y1 is 2 equals m, which is slope, 8, x minus x1 is 1. Cool. Let's go ahead and isolate y. Y equals 8, x minus 1 plus 2 to make it an equation of a line. Okay, cool. Now that we've gotten that, this is like your answer for part A. Let's move on to part B. Part B. Use the tangent line equation from part A. So we have this equation. If your equation was wrong, like if you did this wrong in part A, that's okay. You still want to use whatever you had up here. Like even if you're not confident, take what you had in part A. If it says use your equation from part A, take whatever you had in part A and then do something with that to answer part B. If it's like telling you to do that, they will give you credit for part B if you use what you had from part A, even if it was wrong. But you'll just get the credit for part B, right? If you do it right. Okay, cool. So use the tangent line approximation from part A to approximate f of 1.1. So a lot of students stress about this. They're like, oh my gosh, what is this asking me to do? It's saying that you're going to imagine that you're finding the value at x equals 1.1 on f, and you're just going to use this tangent line, even though it's not f, you're going to use this tangent line and say okay, f of 1.1 is approximately the tangent line at 1.1. So you're just going to plug in 1.1 for x. So we have is approximately 8, 1.1 minus 1 plus 2. And remember, you can leave your answer unsimplified. So I would leave my answer like this. We are done with this part. There's our approximation for f of 1.1. Given that f of x is greater than 0 from 1 to 1.1, is the approximation for f of 1.1 greater than or less than f of 1.1? Explain your reasoning. Okay, so for tangent line approximations, let's talk about really quick what, you wouldn't put this on your AP exam. I guess you could. Tangent lines, we're just taking some notes. So how would we know if our tangent line is a greater than or less than approximation? We would know based on the concavity. This tangent line is an over approximation because it's above the function. This tangent line is an under approximation because it's below the function. So to answer the second part of part B, we need to know about the concavity of the function that our tangent line is on. Our tangent line is on f. So we need to know about the concavity of f of x. Okay, and then we need to think about what tells us about the concavity of f of x. The second derivative. Or in this case, they called it this. This is going to tell us, so we're going to look at this. It's going to tell us about the concavity of f. Okay, this is the second derivative. So we need to go back up to our question and see, did they give us any information about the second derivative? Here is the second derivative. Does it tell us that the second derivative is, we need to check this and check the sign, right? Positive means concave up for f, and then negative means concave down for f, right? So, doesn't mention anything about the second derivative being positive or negative. I'm reading through. I don't see anything specific about the second derivative being positive or negative. So, what else was given to us? Where was our tangent line drawn? A tangent line at x equals 1.1. This tangent line that we're drawing on, like, whatever our f curve looks like, we don't know if it's a concave up or down yet, it's happening at x equals 1.1. So, let's plug in 1.1 to the second derivative. So, at x equals 1.1, d squared y dx squared. Well, actually, you could also let's plug in a whole point. Because look, this second derivative has y's and x's, right? What are we approximating? We're approximating f of 1.1, but that's going to be really close to f of 1 and f of 2. So let's check. If we were to f of 1 is going to be really close to 1.1. So let's just go ahead and plug in this point, 1, 2. So we're going to say d squared y dx squared at the point 1, 2 equals, and then we are not going to actually calculate this. I'm going to write it out just so you can see what I'm doing. 3x is 1, and then y is 2. Okay, cool. This would be the second derivative at x equals 1, which is very, very close to 1.1, right? So we don't care about the actual value, right? We're just trying to check is the second derivative positive or negative. This is going to be positive. So this tells us f is concave up. So the tangent line that we found here, that we approximated, has to be below. It's below f of x. So this is how we would finish the answer to this question. Since f of x Actually, you probably need to say since d squared y dx squared, the second derivative, is positive at x equals 1.1, f of x is concave up, so the tangent line approximation, and then it's asking, is this approximation greater than or less than? The tangent line approximation is less than f of 1.1. And that's how we would finish that one off. Okay, let's go to the last part, which should look the most familiar, but it's a tough one. So we're going to do this one together. The last part says, find the particular solution. Let's see, find the particular solution, y equals f of x, with the initial condition, f of 1 equals 2. So this is what we've been doing. So we need to go through all those steps to find the particular solution. So let's start with the first step, which is separation of variables. We need to get all the y's on one side, all the x's on one side. We're trying to find this particular solution. Really quick, let's go back up to the top. It says that y equals f of x is a particular solution to the first derivative. So let's go ahead and start with that first derivative equation. We're going to start with dy dx equals xy cubed. And then let's do all of our steps. Separation of variables. We're going to multiply dx on both sides, times dx times dx. Cross them out on this side. We have dy equals x y cubed dx. I'm going to divide this y to this side, so we have 1 over y cubed dy equals, let me get some more space, 1 over y cubed dy equals x dx. Okay, next step, integrate. So now we are going to do the integral on both sides, take an integral on both sides. This is y to the negative 3, so the integral is going to be y to the negative 2 over negative 2 equals x squared over 2 plus c. Okay, so remember how on the last DiffyQ, or the last FRQ, I keep calling the FRQs DiffyQs now. On the last FRQ, we said that we can isolate y. We can isolate y first right here, or we can also plug in our initial condition first. We're allowed to switch those steps. So here, I'm going to show you why it would actually benefit us to plug in our initial condition here. So it's easier to plug in initial, I'm going to say IC, initial condition first, before isolating y. So now let's do that really quick. And y'all, you might not notice that it's easier until you like isolate y and then it looks like a crazy big mess. So if you isolate y first, which that might happen, that's fine. But you'll see, like once you plug in the initial condition, you'll see, holy smokes, this is messy. And I can show you that in a second. But first, let's plug in our initial condition. So we had the point 1, 2. So we're going to plug in 2 for y. So actually, you know what, y'all? I know this is very annoying. I'm going to go back and just write this like to where it's mathematically nice. So this is the same as negative 1 over 2y squared. True? I'm not doing anything fancy. X squared over 2 plus c. Okay, so now I'm going to plug in my initial condition. I just didn't want to plug in with a negative exponent. Okay, here we go. We have 1 over, and we're going to, negative 1 over 2, and then instead of y, we're going to plug in 2, and then we have squared equals, and instead of x, we're going to plug in 1. So let me put in that 1 squared plus c. Okay, so now that we've done that, we need to go ahead and like isolate c to solve for c. So we have negative 1 over 2 times 2 squared. 2 squared is 4 times 2 is 8 equals 1 half plus c. I need to subtract 1 half on both sides, which is I need to get a common denominator. 1 half is the same as 4/8. So we're doing negative 1/8 minus 4/8. That turns into negative 5/8 equals c. All right, cool. Negative 5/8 equals c. Let's like hold on to this. This is not our answer. Sorry, I'm like trying to make it to where it pops out, but I did a horrible job. We just are going to have to plug that back in eventually, right? So now let's isolate y. Let's go back to isolating y. We still have to do that step. So we would multiply y squared on both sides. So times y squared, have that in parentheses. And you would get negative, y squareds cancel on the sides. You have negative 1 half equals x squared over 2 plus c times y squared. Divide by x squared over 2 plus c. Remember, we're trying to isolate y. So here's what we're going to do. When you divide this x squared over 2 plus c, and then you take the square root, we're going to leave it real ugly. We're going to say y equals, remember we take the positive square root, negative 1 over 2 divided by x squared over 2 plus c, and we wanted the positive square root. And then let's plug in c. So we're going to say, oh, that's where we went wrong, y'all. I think I plugged in, oh no, that's not right. Okay, who cares? Y equals, we can still make this positive, but we have to flip this still. So we get, actually, you know what, let's just leave it. Who cares? I think AP will take it. Negative 1 half over x squared over 2 minus c was 5/8. Let's leave it like that. This is the same thing. It was just really ugly, and I was trying to like make it look prettier by doing algebra, and I shouldn't have. And I also ran out of room and time. I don't want to waste y'all's time. So we're going to leave it like this, and let's count up our points now. I'll make a better answer key, and I'll like post that in your OneNote. Okay. Here is their answer key. So for the first problem, you get 1 point. 1 point for your answer, and 1 point for actually finding the slope. So 1 point for the slope, 1 point for the equation. For the second part, you get 1 point for your approximation, which is this part, and 1 point for your conclusion. So let me mark these really quick. 1 point for your approximation, 1 point for your conclusion. That's like this, since the second derivative is positive, yeah, and the concave up thing. And then for the last part, again, the diff EQ parts are worth 5 points. So you get 1 point for separating your variables. Oops, that's actually here. You get 1 point for 1 point this time for taking both of the integrals correctly. So 1 point for both of these integrals, and then they still gave you 1 point for the c, for the constant. And then 1 point for using the initial condition, which is what we did over here. And then 1 point for solving for y, which was a struggle for me. But I bet you could have actually done it better than me. So 1 point for actually isolating y correctly. All right, that's it for today. Please work hard on your mastery check. Make sure that you can do these problems, because again, I can't stress it enough. They're worth a lot of points on the AP exam, and it's worth getting at least 4 of these points. I mean, 4 out of 9 5 out of 9 is what we're shooting for to pass, but 4 out of 9 could potentially be a pass on the AP exam. So work hard to learn these steps and practice using your mastery check. Bye, y'all.